Now, in today's class, that will be our 9th class on transport phenomena. We will discuss the differential mass balance. Differential mass balance. The other name of this differential mass balance is the equation of continuity. Equation of continuity. As I have told you in the previous class that the modeling of a fluid flow can be described through the 3 steps. First, you should consider or first you should decide that what is the basic principle that you are going to use, then select the proper control volume and apply that fundamental principle over the entire control volume. You will get an equation embodying that principle, and you will get the momentum, you will get the equation basis of fundamental principle. So, as a first application to that, we will try to develop an equation which is called the differential mass balance, and which is based on the principle of conservation of mass for the fluid element. So, the basic principle here is that in the differential mass balance is basic principle is conservation of mass, that is the fundamental principle. Now, let us take let us assume control volume in the fluid flow having delta x, delta y, delta z as quarter minus edge lengths, along x, y, z axes respectively. Definitely, this control volume will be a parallelopiped in nature or cuboid in nature. So, let us assume here a volume. First, draw this control volume, or better to draw first the x axis. Better to draw the first axis. Let us suppose this is the x axis, this is our y axis, and this is our z axis. Okay. This is the Cartesian coordinate system through which, by the application of which, we are going to obtain an equation over a particular control volume, which can be extended for the entire flow volume to have a equation similar to the modeling of the fluid flow. That how the equation of continuity or the equation embodying the fundamental principle of conservation of mass, how it can be obtained for the entire fluid bulk by taking this differential element into consideration. So, I am drawing the rectangular parallelopiped here, cuboid here, this. Now try to label the different mass which is entering to the fluid element, entering through this volume element and leaving this volume element. So if I am taking the x direction, then the plane perpendicular to the x direction, that is the yz plane, the both sides of yz plane should be taken into consideration. If the fluid enters through one face perpendicular to the x axis, that is the first yz plane, then you have to quantify that how much fluid mass is entering, and at a distance delta x, this is the delta x, this is the quarter minus length delta x, this is the delta y on the y axis, and this is the delta z along the z axis. So if I am considering, let us suppose this direction, that is the x direction, so the quantity of mass which is entering is rho Vx, the perpendicular to the flow direction, that is the yz plane. So the area of this plane, that is the rho Vx delta y delta z. Similarly, if I am taking y direction into consideration, then this is the positive y direction. So here rho Vy delta x delta z, and if I am keeping this z direction, then here it should be rho Vz delta x delta y. Keeping the fluid mass which is leaving out of the system by showing some other color, so this should be equal to, this should be the rho Vx, the value of rho Vx at to x, rho Vy value at y equal to y, and rho Vz value at z equal to z. Similarly, this quantity which is fluid mass which is leaving, that is the rho Vx, the value at x plus delta x, x plus delta x into delta y delta z. Similarly, for the fluid mass flowing along the y axis, the quantity of fluid mass which is leaving out of this control volume, that will be equal to rho Vy, the value at y plus delta y into delta x delta z. And similarly along the z axis, this axis, that should be equal to rho Vz, the value at z plus delta z into delta x delta y. So as per the diagram, the fluid masses entering and leaving the control volume, have been shown. Now here I would like to emphasize one thing. Let us consider two different points. Let us suppose this is your point P. Having the coordinate x, y and z. With reference to this particular Cartesian coordinate system, I am assuming that this is a point P having the coordinates x, y and z. Let us suppose I am assuming another point. Let us suppose this is the Q. This has the coordinate x plus delta x into y plus delta y into z plus delta z. What is the peculiar characteristic about the point of P and Q? You can observe. So P is the point at which all the phases which are see the point number P. This is the meeting point of this surface, this surface, and also this surface. These are the three. This surface, this is your delta y into delta z, that is yz plane, delta x into delta y, that is the xy plane, and the delta x delta z, that means this plane. These are the three planes at which this plane as well as this plane and this plane, that is behind the blackboard. These are the three planes that are meeting at the point which are receiving fluid mass, whereas Q is the meeting point. Q is the meeting point for the phases through which, now consider this Q. This is the one surface through which this fluid mass is leaving. This is also another surface through which fluid mass is being leaving along the z axis, and as well as through this surface, this one, this is the also another surface, this and this, through which the fluid is being leaving through this phase. So the Q is the meeting point of the phases through which fluid masses are leaving the system. Applying the principle of conservation of mass, the equation can be written as mass of fluid entering the control volume, per unit time minus mass of fluid leaving the control volume per unit time that should be equal to how much? That should be equal to the rate of accumulation of mass in the control volume. That should be equal to rate of mass accumulating in the control volume, So the basic fundamental equation which will lead to the derivation of the principle of conservation of mass for the fluid flow under consideration, or you can say the equation of continuity for the present case, will be derived. or you can say, let us suppose mass of fluid entering minus mass of fluid going out, that is equal to rate of accumulation of mass in the control volume. Let it be question number 1. Now try to evaluate all these quantities separately and put it there in order to have the differential moment mass balance or continuity equation. So, now start the derivation part. Mass of fluid entering the control volume per unit time, that will be equal to how much? Rho Vx at the value x equal to x delta y delta z plus rho Vy y delta x delta z plus rho Vz z x delta y. Let it be question number 2. Similarly, mass of fluid leaving the control volume per unit time. Here I would like to emphasize one thing, how this quantity stands for the rate of mass. So, let us suppose I may explain this: rho Vx delta y delta z, rho is 3, V that is the t to the power minus 1, this is L, that is equal to m, L raised to 1, t raised to the power minus 1, that can be written as m L t to the power minus 1 here you have to assume that is equal to rho minus 1 divided by L square, that is equal to mass into velocity divided by area. So, here So, try to evaluate this delta dot V, because this is dot product of two vectors. Now, let us try to evaluate this delta dot V, delta vector dot V vector, that is equal to I deva by deva x plus z deva by deva y plus k deva by deva z into, that is the dot, Vxi plus Vyj plus Vzk. So, from the normal principle of the dot product of vector, that can be written as deva by d, or we can write deva dot rho v, because the fact the multiplication of a vector by a scalar is still a vector quantity. So, deva dot rho v, that should be equal to I deva by deva x plus j deva by deva y plus k deva by deva z into rho vx I plus rho vy j plus rho vz k. So, that may be written as deva by deva x into rho vx plus deva by deva y into rho vy plus deva by deva z into rho vz. Let it be equation number 6. Now, taking the help of the equation number 5 and 6, thus from equations 5 and 6 we can write minus del dot rho v vector, that should be equal to the time derivative of rho with respect to t, or we can write deva rho by deva t plus del dot rho v vector, that is equal to 0. This equation number 7 is called the equation of continuity. So, this equations number 5 and 7, equations 5 and 7 are the general forms of equation of continuity. The expression that we have gone through is the differential mass balance for a laminar flow. That means you can easily distinguish the velocity components along the x, y and z axes, and you are easily quantifying them as Vx, Vy and Vz. Now, the question arises, if the same equation needs to be applied for a turbulent flow, what are the necessary arrangements that are required in the equation number 5 or 7. So, for turbulent flow, equation of continuity for the turbulent flow, equation of continuity for in the case of turbulent flow, in the cases of turbulent flows, since velocity changes at every point in the flow with respect to its magnitude and direction both, that means if I am considering the flow of a fluid at a high Reynolds number, then at each and every point the direction of the flow will changing, the magnitude of the flow is also changing. Such type of flow behavior is what is called as turbulent flow. So, magnitude and direction both. In such circumstances, average velocity needs to be taken. That means Vx, Vy and Vz need to be represented in terms of their respective average values, average values such as Vx bar, Vy bar, Vz bar. So, if I am representing the delta V vector for a turbulent flow, if I am representing the delta V vector for the turbulent flow, so we need to write I Vx bar into I plus Vy bar into j plus Vz bar into k. So, rho V vector for the turbulent flow, that will be equal to rho Vx I plus rho Vy j plus rho Vz k. Hence, equation number 5 can be reproduced as means keeping the turbulent flow in view. So, this equation number 5 can be reproduced as del by rho by del by t, that should be equal to minus del by del by x rho Vx bar plus del by del by y rho Vy bar plus del by del by z rho Vz bar. Let it be question number 8. In terms of vector operators, in terms of vector calculus operator, this equation may be represented as del by rho by del by t, that should be equal to del into rho v bar vector this, or deva rho by deva t plus del dot rho average v vector, that should be equal to 0. So, the equations number 8 and 9, equations 8 and 9 are called continuity equations for turbulent flow, or continuity equations for turbulent flow. The next topic is the equation of continuity for incompressible flow. Equation of continuity for steady and incompressible flow. Incompressible flow. The meaning of incompressible flow is that the density of the fluid does not change with respect to time. It means the partial derivative of the density with respect to t, that should be equal to 0. Incompressible flow means this quantity deva rho by deva t is equal to 0. Hence, steady state equation of continuity can be given as because this quantity that is equal to 0. So, I am writing here deva rho by deva t plus del dot rho v vector, that is equal to 0 for the laminar flow, and for the turbulent flow this del dot rho v average vector, that is equal to 0, because of the fact this quantity is equal to 0, because the incompressible fluid flow is there. So, expanding these equations, we will obtain the equation of continuity for the steady state incompressible fluid flow. So, del dot rho v vector, that is equal to 0. It means deva by deva x rho vx plus deva by deva y rho vy plus deva by deva z rho vz, that is equal to 0. Since rho is the constant quantity, so the form of the equation is deva bx by deva x plus deva vy by deva y plus deva vz by deva z is equal to 0. This is the equation of continuity for the laminar flow. Considering the second one, that is the del dot rho average v vector, that is equal to 0. So, the form of the equation will be, let it be equation number 10. So, deva v x average divided by deva x plus deva vy average divided by deva y plus deva vz average divided by deva z is equal to 0. So, the equation number 10 and 11 are the continuity equation for incompressible flow. Continuity equation for incompressible flow. The equation of continuity has very important fundamental application. Let us suppose I am giving you one example. Let us suppose this is the cross section of a conduit, and the cross section suddenly decreases to a smaller value. Okay. Let us assuming this section as section number 1 1. I am assuming this section as section number 2 2. Let us suppose 1 1 and this section is 2 2. Let us suppose area is here A1, here area is A2, here the velocity is V1, here the velocity of V2. Now, the quantity which is entering through this conduit, that will be entire quantity will get dissipated through this opening also. That means, we can say A1 into V1, that should be equal to A2 V2. So, V2 by V1, that is equal to A1 upon A2, is it not? Since A1 is greater than A2, so the A1 by A2, that should be equal to greater than 1, that should be greater than 1. So, imply that V2 by V1, that will be greater than 1, imply that V2 is greater than V1. That means, the fluid velocity will experience a larger magnitude at this cross section. The initiation of the blood pressure in the human body is a result of the continuity equation. Due to the accumulation of the fat layers at our veins and arteries, this diameter is going to reduce. It is further reduced if more and more LDL is going to be deposited here, that giving rise to a decrease in the diameter, and hence the velocity increases, and a man feels that his blood pressure is being increasing. So, this is the application of the equation of the continuity in our day to day practice. Thank you. In the next class, we will see the differential momentum balance or the equation of continuity. Thank you.